So check this out. If I blow on the underside of a piece of paper, it causes the paper to go up. That is boring and not very surprising. The molecules are ricocheting off the paper and creating an upward force on it. But if I blow over the top of the strip of paper, it still causes the paper to go up. Interesting, huh? Similarly, if I blow on a candle, the flame flickers away from me. But if I put a card in the way and blow on that, it flickers toward me. The moving air is causing lower pressure. If we want to look like a Jedi, we can take advantage of that by taking a hairdryer looking thing, putting a ping pong ball in it, and blowing air all around the ball. As the ball tries to move out of the way of the stream, it gets caught and brought back because it's in the lowest pressure position. You can try this at home with a ping pong ball on a string and a stream of water out of your faucet. It really does work.
In the 1700s, Swiss physicist Daniel Bernoulli figured out that this relationship between the speed of the fluid and the pressure, and that the speed creates lower pressure, is a pretty interesting thing. This is a fundamental piece of science that we use for lift in airplane wings. It's why your shower curtain might attack you when you are when you first turn on the water in the morning. It's the water starts to flow. That causes faster moving air inside the shower, and so the slower moving air on the outside pushes inward at you. A passing tractor trailer going by, if you're coming this way and it's going that way, it can actually pull you towards their lane because that faster moving air actually causes a pressure difference that is noticeable on your car. Tacking for sailboats, all sorts of things use this idea. And we can actually take that idea and derive what we call Bernoulli's equation, which we're going to do a lot of work with, so you definitely want to pay attention. Check this out.
Suppose we want to pump some water from a lower position to a higher position. The amount of work we would have to do would equal the change in kinetic energy of the water plus the change in the potential energy due to gravity. Well, we know that work is force times distance, and force is pressure times area, and area times distance is volume. So the work we do is going to be pressure times volume. Now, we are doing some work in order to move the fluid, but the fluid is doing some work on the atmosphere or the other fluid that's in the way, so the total work is going to be the positive work done minus the negative work done. That's P1V minus P2V. The total change in kinetic energy is just going to be the difference in those two terms, and the change in the total potential energy due to gravity is also going to be the difference in those two terms. Let's substitute all of that into work equals change in kinetic energy plus change in potential energy. There we go. Now let's put all the initial state stuff on one side of the equation and all the final state stuff on the other side. The last trick we're going to do is we're going to divide by the volume because it's a constant, and that turns our masses into densities. And this whole equation is now a matter of pressure rather than one of energy, although it really does come from the work-energy theorem. Either way, there you have it, Bernoulli's equation, which you can find on your reference tables.
A corollary to Bernoulli's theorem is called Toricelli's theorem, developed by Evangelista Toricelli, and it says that a jet of water will rise to the height of its source. So if you have, for example, an artesian well, so you have a mountain, and inside that mountain is a reservoir of water, and down here you've got a house, and you dig a well, then the pressure from that well will shoot the water right up to the level of its source. That means it has to have the free fall velocity of v equals square root of 2gh. That is a funny thing on the AP exam because you're allowed to use it as long as you can name it. So that's Toricelli's theorem. You should know it. Let's take a closer look at some of those things I'd mentioned earlier, like vascular flutter from arteriosclerosis, airplane wings, and tacking sailboats. Check this out.
A lot of people know that cholesterol is bad for you, but they don't know why. Well, here it is. When you have a blood vessel that has been partially constricted because of plaque buildup from cholesterol, when the heart tries to pump blood through that artery, it goes faster to get through. That's continuity. Well, the faster speed means that there's lower pressure. That's Bernoulli's principle. When the pressure gets low enough, it can drop so much that the surrounding tissue will compress the artery and make it so that it closes completely. That forces the blood flow to stop, which causes the pressure to go back up because the velocity is now 0, and then the whole thing starts again. And this happens really fast. So instead of having a nice whoosh of blood through that area, you get this start, stop, start, stop, start, stop, start, stop, which is really quite bad for you. And if it happens severely enough, we call it a heart attack. So watch your cholesterol, kids. Next up is the airplane wing, which has a sort of elongated teardrop shape. When the airplane moves into the wind, it creates in its own reference frame a wind passing over the plane. The flat bottom part of the wing isn't as long as the top rounded part, and so air has to move faster to go that longer distance. Faster air means lower pressure, and this pressure differential creates lift. It's worth noting that that's generally not how planes stay in the air. They stay in the air by air deflection. Air ricochets off the bottom of the wings and gets pushed down, and the reaction force is that the air pushes the wing up. But in order to get off the ground in the first place, it's all Bernoulli. Tacking is remarkably similar. You can change the shape of the sail to be somewhat similar to an airplane wing. You can use this to then sail not directly into the wind, but at an angle to it. You can flip the direction of the sail to turn your zag into a zig, and then repeat the process to zigzag your way in the direction of the wind as a net velocity. So there you have it, that's fluid physics in a nutshell. We'll wrap up this unit in the next video with some sample problems. See you there.